The next session I would like to introduce is Seiichi Nagihara with for topic the heat flow measurement planned on the Blue Ghost mission to Mare Crisium. Please, Seiichi, all yours.
Okay. Hello. Do you see my slides okay?
Yes.
Okay, thank you. All right. Let me switch to, here you go, presentation mode. So I'm going to talk about this Blue Ghost mission. So then, you know, the name Blue Ghost may not be very familiar to some of you, but it's one of the Eclipse missions. So it's slated to fly in year 2023. Then earlier this year, NASA selected Firefly Aerospace as the lander provider and also the operator of the mission. Then we are going to Mare Crisium. Then again, we're going to land there sometime during the second half of 2023. Then the lander is not going to survive lunar night. So our time for the surface operation is going to be roughly the same length as the lunar day. So then we're going to have 10 NASA supported payload instruments. Then I'm the PI of one of those instruments called Lister, which is a heat flow probe. Then I understand that the Firefly has its own sort of clients who are flying with these NASA supported payloads to go to Mare Crisium. So they're having 2 successful heat flow measurements done on the surface of the moon. So those were by the Apollo astronauts, right? Then so at Apollo 15 sites, the heat flow there is 21 milliwatt per square meters. Then at Apollo 17 sites, heat flow is a bit lower, 16 milliwatt per square meters. Then about 20 years ago, Victorek and Phillips proposed that the Apollo 15 site is within the so-called PKT, where the heat producing elements or radionuclides have a higher concentration in the crust, at least on the surface, right? So because of this heat production in the surface, near the surface, this is probably because of that, the heat flow at Apollo 15 site is greater, right? So then in thinking about, where do you want to get the next heat flow data point, right? Then I guess we need to really think about what we are actually measuring. Then actually, so that we're trying to capture, the heat that originates from the deep interior of the moon, but actually what we are measuring is the heat flow that comes out of the surface of the moon, right? Then so based on what we know about the planetary differentiation, and then also based on what we know about the Earth, right? So we expect the so-called, the vast majority of the so-called heat-producing elements are actually concentrated within the crust. Right. So because of that, okay, so the heat flow we measure at the surface of the moon will be probably greater than the heat that comes out from a much deeper interior of the moon and then through the mantle and flow into the bottom of the crust layer, right? Then we don't really know how much actually the crust generates heat because we don't really know the vertical distribution of the so-called heat producing elements, right? Then, so like I said, so this Blue Ghost mission is go to Mare Crisium, right? Then I think that will provide us a very good opportunity to actually learn more about this thermal structure and evolution of the moon, right? So the general questions we have is sort of first, so does the surface distribution of the radionuclides a good indicator of the surface heat flow? That's what we're kind of sort of assuming, in contrasting between Apollo 15 and Apollo 17 site, right? But again, but we don't really know how vertically these heat-producing elements are distributed, right? Then also, how much heat is really being generated within the crust, and actually how much heat comes from the mantle? Then does these, amount of heat vary between PKT and elsewhere? Right. Then, so the Mare Crisium is more than 1,000 kilometers from the edge of the PKT. Then also, this is one of the place where the crust is the thinnest on the surface of the moon. Based on the Grail data, we estimate that the crust in the Mare Crisium is less than 10 kilometers thick. So because of that, so we think the crust there produces minimal amount of heat radiogenically. Right. So in other words, what we measure, the heat, what we measure on the surface should be very close to the heat that comes out of the mantle and flowing into the crust. So, so that gives us a very important constraint on the mantle heat flow, right? So, so that's one of the reasons we're going to Mare Crisium, want to get a heat flow measurement. Then, of course, this is going to be the first time we're going to try to measure heat flow on the robotic mission, at least on the moon, right? So, so our team has been developing this the heat flow instrument that can fly on the robotic mission. So that's Lister. Then, so this kind of gives you a schematic view of the instrument. So this lander is not the Firefly lander. As you can see, actually it looks more like a Lockheed Martin lander that is used on InSight and the Phoenix. But anyway, so so the instrument housing is going to be attached to the underbelly of the lander, right? Then, so you can see the sort of a lower left, so that's the deployment mechanism. Then this yellow thing, so that's about the size, a little bit greater than the palm of your hand. So it's a very compact modular system. Then, so it spools out a stainless steel tube of about a 1/4 inch diameter, 6 millimeters, right? Then the way that this tube spools out is very similar to the way the tape measure spools out, right? Then at the leading end of this tube, right? So, so we have a hole from which compressed gas of nitrogen comes out, the jet of gas. Then because we are emitting this gas in vacuum, so that's why as soon as the gas comes out of the hole, it expands, right? So we are using this momentum to blow away the regolith clumps. Then, so we use the momentum of the expanding gas. Then also the push by the motor that spools out the tube to actually penetrate 3 meters into the lunar regolith. Then all of our sensors are attached to the leading end of this tube, so we just called it the needle sensor. Then, so on the right side, we have a kind of expanded view, the schematics of that. So, so this needle sensor is about 2 centimeters long and 2 millimeters in diameter. Then it has an RTD in the middle. Then it's got the heater, right? So, so as we try to penetrate down to 3 meter depth, right? So we make a stop roughly every 0.5 meters. Then at every stop, we make temperature and the thermal conductivity. We measure temperature and the thermal conductivity of the regolith. So when the probe finally reaches the 3 meters depth, so we're going to have a temperature and the thermal conductivity data points every 0.5 meter. Then we get thermal gradient, then we get the thermal conductivity, then you multiply the two, then we get that conductive heat flow at the location, right? Then in deciding on 3 meters, so we are using the lessons from the Apollo experiments, right? So yeah, so because of the Apollo experiments, we have a pretty good idea of what the thermal conductivity of the regolith is. Then we also roughly know what kind of heat flow value we should expect, right? So so the uppermost 1 meter of the regolith, the temperature there is going to be constantly changing because of the influence of the insolation, diurnal and annual insolation cycles. Because of that, the temperature in the first meter or so, it's going to be constantly changing. But below that, temperatures there is going to be stable, right? So the thermal gradient there should be representative of the heat that comes out from the deeper interior. So our objective is to get 4 or 5 good quality temperature and thermal conductivity measurements in the zone of the temperature stability to go after the heat flow. Right. So we are planning to deliver the flight unit in about a year from now. Then, so we are still pre-CDR. So we are still conducting a number of tests, right? So those tests can be kind of categorized in sort of in two. The one is to optimize our pneumatic drilling system, right? Then the other is to optimize our sensor subsystem. Then, so on the left side, I'm going to kind of run a little video. So before I do that, I'm going to give you, just put it in the context for you. So, so as you can see, this deployment mechanism, which is uses a sort of a transparent material so that we can actually see how the internal mechanism is moving. Then, so that's set up in a vacuum chamber. So that's about 3 meters tall in this case. Then so then the deployment mechanism is just attached near the top of that chamber, right? Then as you can see, the stainless steel tube kind of spooling out toward the lower end. Then the bottom 2/3 of the chamber is filled with lunar regolith simulant. Then as you can see, there's already hole created, so we have already kind of started down on into the simulant. Then the diameter of the hole is about 5 centimeters.
Seiichi, we're actually right up at the end of the time, so can we kind of get the last kind of slides through?
Oh, really? Oh, okay. Sorry, I didn't know. Okay. All right. So let me just show you this video. Just okay, to how it goes. All right. Here you go. So that's the power of the expanding gas. Then you can see the mechanism turning, right? Then on the right side, so we are just testing the sensor system there. So let me just move on quickly. So then, you know, one of the questions I get asked often is, so what would you do if you run into rocks, right? So then, of course, as you can see, the pneumatic system can easily blow out small nuggets, right? Then the other mitigation we are employing is to try to land in a place that has the lowest chance of running into rocks. So that's why to do that, so we are using the Diviner rock abundance maps and also some radar returns that tells you more information about the texture of the regolith in the subsurface. Then so we are kind of working with the NASA people in selecting landing site that also satisfies the condition of lowest chance of running into rocks. All right. So yeah, so let me just stop here. I'm sorry for running over the time.
Thank you very much, Seiichi. Don't apologize. It's a very interesting topic, and thank you so much for your presentation.